Hello, Boys State University. Thank you very much for giving me a chance for presenting a video. I am going to present a video show on relations. I am going to solve a problem on relations. First of all, what is a relation? A relation is just a subset of a Cartesian product of two sets. Given any two sets by axiom of set theory, there exists a set called Cartesian product of these two sets, and by the axiom of subset, there exists a subset of this Cartesian product. And axiomatic set theory also proposes that empty set exists, and because empty set exists, we can form non-empty sets using these empty sets. So non-empty sets also exist, and so the Cartesian products also exist, the subsets of the Cartesian products exist, and a relation also exists. Now there are some properties of relations, like reflexivity. What is this reflexivity? When a relation is a subset of Cartesian product of a set with itself, we can always obtain a Cartesian product of set with itself. So a relation on Cartesian or on a set or a subset of a Cartesian product of set with itself is called reflexive if all the elements, every element of the set is related to itself by this relation. Then it is called reflexive. It is called symmetric if x is related to y, then y is also related to x. Then it is called symmetric. It is called antisymmetric if x is related to y and y is related to x, then x and y must be equal. And the relation is called transitive relation if for any three elements in the set x, y, z, if x is related to y and y is related to z, then x is related to z. Now we are going to solve a problem on relations, and first we will try to answer a crucial question which occurs in many people's mind, many students' mind, that is, yes, when a relation is reflexive, symmetric and transitive, when it has all these three qualities, then it is called an equivalence relation. Now some students ask, is it necessary that reflexivity should also, there is reflexivity redundant? That means can't a relation be just symmetric and transitive and yet an equivalence relation? We will try to answer this question also. So let us see the video show. Just give me a second. So, hello, my name is Vipin Musale, and we are going to see some show on relations. So, is reflexivity redundant for equivalence? So, are symmetry and transitivity enough for a relation to be equivalence relation? Now, let us see. Suppose R is a symmetric and transitive relation. R is a relation such that it is symmetric and transitive. So if x and y are any elements, if xy, Cartesian product, the ordered pair xy is a member of R, or x is related to y under R, then y is also related to x under R because it is a symmetric, it is going to be symmetric. And now this also gives us x is related to y, xy belongs to R implies xy belongs to R, P implies P, yes, it's a true. So if xy belongs to R, then the ordered pair xy belongs to R and ordered pair yx also belongs to R. That means we have these two ordered pairs belonging to R. And see, by using the transitivity, now we can always conclude that x comma x belongs to R, that is x is related to itself. So does this mean that R is also reflexive? No. Not at all. Why? Because the properties of symmetry and transitivity are conditional. What does symmetry says? If x is related to y, then y is also related to x. If x is related to y, then y is also related to x. This is the conditional statement. And transitivity also says if x is related to y and y is related to z, then x is related to z. This is also a conditional statement. This means even if we take an empty subset of a set A cross A, okay, then also this subset will satisfy, this relation will satisfy the properties of symmetry and transitivity, but will it satisfy the property of reflexivity? No. Reflexivity is a categorical statement. Property of reflexivity is categorical statement. For all x belonging to A, if x is related to itself, if x comma A, the ordered pair x is member of this relation, then only we can say that the relation is reflexive. So reflexivity is not redundant. Okay. So for relation to be equivalence relation, it has to be all the three: reflexive, symmetric, and transitive. Now let us solve this problem. So let R be a relation on the set of real numbers. It is given by this: the set of all ordered pairs of numbers such that the product of the two numbers in the pairs is non-negative. Okay? X is related to y if x into y is greater than or equal to 0. So is it reflexive? Yes, quite simple, right? No hassles. X for all x belonging to R, x into x, that is x square, is always greater than or equal to 0, and therefore all these ordered pairs x comma x, they belong to R. So R is reflexive. Is R symmetric? Yes. No hassles here also. xy belonging to R, if xy is an element of R, their product has to be greater than 0, greater than or equal to 0, and by the commutative property of the multiplication, yx is also greater than or equal to 0, and therefore the ordered pair y comma x also belongs to R. Thus x is related to y means y is also related to x under this relation. So it is a symmetric. So for all ordered pairs xy, yx also belong to R. Now is it antisymmetric? What is antisymmetry? If xy belongs to R and yx also belongs to R, then in that case x must be equal to y. Now here we give a counter example. 2, 3 belongs to R because the product is greater than or equal to 0. Similarly, 3, 2 also belongs to R. Okay, because for the obvious reason that the product is greater than or equal to 0, but we can easily say that 2 and 3 are distinct, they are not equal. Okay, so we can't say this is antisymmetric because there exist two real numbers x, y such that x is related to y under R and y is also related to x under R, but still x and y are not equal. This statement is not true. The statement which defines the property of antisymmetry is not true here. So this is not antisymmetric. Okay, is this transitive? So if xy, the ordered pair xy is in R and y ordered pair yz also is in R, this implies that the product of xy is greater than or equal to 0 and product of yz is also greater than or equal to 0. So you can multiply if the multiplication of two non-negative numbers is also non-negative. So no problem here also. Now here we apply commutativity, the commutative property of multiplication and associative property of multiplication, and we find that x into z into y into y, this product is also greater than or equal to 0. Now we find that what is there inside the parenthesis, it is a positive number, because y square of a number, any real number, is a positive. Square of any real number is a positive, yes. No, it is a non-negative. Okay, so many students make this mistake of mixing up with positive and non-negative. And so does this imply that the x into z is greater than or equal to 0? Can we just divide by the y square both sides and yet the inequality remains unchanged? And so can we conclude that x is related to z also? So no, a big no, because here this does not imply that x, product of x and z, is non-negative. First of all, y cross y we do not know. Y could be 0 also. Okay, so we just can't divide both sides by the y square and conclude that x is related to z. So we just can't conclude that x is also related to z. Now here we give a counter example. See, the 1 into 0, it is non-negative. So also 0 into minus 1 is non-negative. So 1 comma 0, 1 is related to 0 and 0 is related to minus 1, but yet 1 is not related to minus 1, as their products is not non-negative, the product is negative. Okay, so there exists three real numbers x, y, z such that they make this property, the statement of property of transitivity, false. Okay, and for this reason we can't say that the relation is transitive. So thank you very much for watching this show. Thank you for giving me the chance to present this video. Thank you so much.